The answer is, who watched Jeopardy last night? Who watched it? Who paid attention to it? You can watch it on YouTube, I think, tonight. And Watson gets it. You got it right. So maybe I don't have to discuss it, but let me just do it quickly for the camera. Ready? Okay, first of all, everybody got the quiz right. The quiz was, given the masses and velocities of two things, what's the linear momentum of the system? L stands for linear momentum. Starting today, we're going to put arrows on top of these things, and they're not all going to be in one dimension. The linear momentum is the sum of the linear momentum of the parts. So A is correct. This quantity here is an interesting quantity, but it's not the linear momentum of the system. It's the velocity of the center of mass of the system. This thing is another way of saying this thing. And if you mix these quantities up and do some algebra, you can see how they're connected to each other. If you have any doubts about it, that algebra, you should do it, because the same algebra is going to apply in 2 dimensions, 3 dimensions, and for multi-particle systems. So just seeing the relationship between these quantities is important. But for our purposes here, this is the right answer, this is the right answer. This is not the right answer, but it's an interesting quantity, so it's 2 or 3 of the above, namely these two. Any quick questions about this quiz? Okay, so now we're going to go on and talk about particle motion in 2D. So we get to use our computer skills and our calculus skills, and now we're going to mix in the vector skills a little bit. So we're going to do particle motion in 2D. In fact, a bunch of old skills are going to come crashing in, which you can use more or less. So the big equation we're working with is what we call the linear momentum balance equation. And this is the equation that the sum of forces on a system is equal to the rate of change of linear momentum of the system. So that's probably the most important equation in this class, or it's one of 2 most important equations. The other one is that the sum of torques on a system is the rate of change of angular momentum. But we're not getting to that yet today. So now we want to understand what these different things mean. This means the sum of forces on the particle. And this is the rate of change of linear momentum of the system. So L is equal to the linear momentum, which is equal to the mass times the velocity. So this equation here is equal to also the mass times the acceleration. And what do you mean by the mass? You mean the mass of a particle. What's a particle? Sometimes you think of a particle as a dot. But what's a dot? How big is a dot? So a dot under a microscope doesn't look like a dot anymore. And people take things like the sun and model them as particles. And what do you mean the sun is a dot? The sun is a very big thing. It's bigger than anything you're going to work with in engineering. So what do you mean by a particle is something where you don't pay attention to the motion relative to of the parts relative to each other. So long as you don't pay attention to the motion of the parts relative to each other, you think of it as a particle. And this includes rotational motion, because in rotational motion, relative to a fixed frame, there's motion of the parts relative to each other. So a rigid object is not a particle if you're paying attention to the rotation. Okay, and then what do we mean by the force? We can say this force is the net force, and this net force we can call F, and we can think of this F is going to be determined somehow according to some rules. It could be that the force depends on where you are. For example, if it's a gravity force, it could depend on how fast you're going. If it's a drag force, or it could be depend on time if it's some force which is applied by something which is controlled, say a rocket engine going on or off. So if we want to just put examples here, we could put F is equal to F of R. That would correspond to, say, gravity, or maybe a spring or something like that. We could have another example would be F is equal to F of V, and that would correspond to, say, a drag force, which could be proportional to speed or proportional to speed squared. Or we could have F is equal to F of T, and that would be, say, some controlled force, like a rocket engine or some other system which is moving some way and somehow applying some force which depends on time, or it could be any mixture of those things. So this is a general case, and this is just like in one dimension we had x, v, and t. So we had like a spring force, or a drag force, or an applied force which varied in time. Now the things which vary with position are varying with x and y position, and things with velocity have two components to them as well. So this is the part that sort of is the challenging part of the course, is paying attention to and understanding acceleration. So this is what will be the hardest part of the course for you, is understanding that one symbol. How is that hard? Well, it's because it's just hard to keep track of how things are moving, especially when you have various parts moving relative to each other. To start with, it's not going to be that hard. We have that the acceleration is the rate of change of velocity, and we have that the velocity is equal to the rate of change of position. So we want to think about this with a graph. We can do this in a way that's sort of component dominant, or a way that's sort of geometric dominant, and you would like to be able to go back and forth between these different points of view. To start with, let's just put the sort of geometric point of view. We want to look at a particle whose position is changing in time, and say the x-coordinate we can call x or x1, and the y-coordinate we can call y or sometimes x2. And since we're going to be working with vectors, we'll have these unit vectors here, and these unit vectors, these unit vectors we can call I, or sometimes we might call it E1, and this one we can call J, or we might call this E2. And then we have this particle which is moving along in time. At one time maybe it has its position R, and this is R at some time of interest, and at a later time it has a different position, and this is then R of t plus delta t, and at all different times it has all different positions, and so the particle is moving along like this, and this is what we call the trajectory of the particle. And the trajectory is represented by R is R of t, but on this picture you can't see how the trajectory changes with time. You can just see the trace that's followed. So two particles could have the same trajectory and different accelerations if they moved along the path differently. Okay, so this is what we mean by position as a function of time when something's moving along, and we want to figure out what do we mean by acceleration. So the key quantity here is that R is changing. So when you go from one time to another time, there's a change in the position, which is delta R. And so what we want to do is understand what the relationship is between delta R and V. So I hate to go backwards here, but it's such a nice spot on the blackboard. The key thing is this definition here, is that the definition of V is the limit as delta t goes to 0 of delta R divided by delta t. And this is a thing which we call R dot or dr dt. Now if we want to write this in components, this position vector R at some time, it has some x component and it has some y component, and the vector R is then written in terms of components like this, or we could write it x1 e1 plus x2 e2, x1 e1 plus x2 e2, and since we see that this derivative works just like the regular derivative in regular calculus, that is all the simple operations like addition and multiplication by scalars work the same with vectors as with scalars, this then becomes x dot I plus y dot j. And if you want to work this out a little slower, it's in the book, but I feel like slow derivations of things like this, you don't, as I said, I don't think you enjoy them any more than you enjoy looking at MATLAB code for a long period of time. Okay, so then we can look at what do we mean by acceleration. By acceleration we mean the derivative of v, which in turn we can think of as r double dot, and then this is vx dot I plus vy dot j, Or we can write this as x double dot I plus y double dot j. And this thing we can think of as Vx, and this thing we can think of as Vy. So this is the basic layout for position, velocity, and acceleration, and for force and velocity. Now, just to give you sort of a little bit more of a geometric flavor of what velocity is, we can make the same way we have a trajectory of position versus time, we can also think of a trajectory of velocity versus time. And we can think of this geometrically, or we could work it out with components. But here's how it goes. We take and make a new plot, and the plot here has as components Vx and Vy. And we plot at every instant in time a vector, which is the velocity vector. So say we're looking at this trajectory here. The velocity here is always tangent to the curve. That's an important thing to remember. Velocity is always tangent to the trajectory. So if you know the direction of the velocity, you know the direction of the tangent to the curve. It starts out with the velocity in this direction, and then the velocity sort of bends over in this direction, and it goes over to this direction, and maybe it goes in this direction, and then down in that direction, and then it maybe goes back up in that direction. And there's a curve that we can draw like this, and this is the locus of the tips of the velocity vector as the particle moves. So it's the trajectory of the velocity as opposed to the trajectory of the position. And this here is the trajectory of position. Now, this is not a particularly important concept. It's not used all that much. It turns out that it is used in the research we do in my lab. So let me just show you an example, just to get to think about it. So the reason to think about it is just to stretch your brains and build some intuition about these things. So for example, and this is only a kinematics example. I'm not yet doing a mechanics example. But we have the kinematics of walking. When somebody's walking along, the simple way to describe walking is to think of your foot as a stick and your body as a point mass, say at your hips. And when you walk, you move in a circular arc until the next foot hits down, and then you move in another circular arc, and so on. And this is the simplest sort of a cartoon of what walking is that you have these sequence of arcs, and where one foot is down like so. So this trajectory here is the trajectory of your hip in walking. And now it's not exactly the trajectory, but there's a model or an approximation of the trajectory of your hip in walking. And to go along with that, we could put an axis here, we could pay attention to some point here, we could call this 0, we could call this the x direction, we could call this the y direction, and here we have this trajectory of what your hip does when you walk. And going along with that, we can make a hodograph, and the hodograph then has the axis Vx and Vy. And let's just start at this position right here. So when you start here, your velocity is tangent to the path. So at point 0 here, your velocity is tangent to the path. So that's approximately that direction. So I'll call that 0. Then what happens is you change over to moving horizontally, but you're going slower because if your energy is roughly conserved, you've lost some potential energy, so you have a slower speed here. So this velocity vector is shorter than that velocity vector. And then eventually you end up going fast again in that other direction. So we have a trajectory along this from 0 to 1 to 2, and that's from 0 to 1 to 2. And then suddenly we're going to jump over to point 3, which is we're going to jump right back here to 3, And how do we do that? We do that along some curve that takes us back up here. So some funny shaped curve. And the details of this curve actually are all important in terms of figuring out the energetics of walking. And this thing is called the, when you change from being on one foot back to being on another foot, is called the step-to-step transition, or the down-to-up transition. So this is a photograph of walking. And why do I show this to you is just as an example to stretch your brains a little bit about what the relationship is between velocity and position. Now, if we wanted to just represent this, with components, we could find the x and y components of position versus time, take the derivatives of them, then we'd have the vx and vy components, and then we can make a cross plot and get this curve. But I think you get some intuition by looking at the curves directly. Now, there's some other key vectors that we want to pay attention to. One is that we're going to define a special unit vector in this direction, and this is called ER, and that's the R divided by the magnitude of R, and that's a unit vector in the R direction. Unit vector in R direction. And what do you mean by the R direction? You mean the R relative to whatever point you're using as an origin. And another key vector that we're going to pay attention to is the unit vector tangent to the path, and that's ET, which is the velocity divided by the magnitude of the velocity, and that's a unit tangent. Okay, so now we have the whole story, in some sense, for particle mechanics in 2D and 3D, and we can go and do an example. So the next thing I want to do is just do an example, and then I'll show you how to integrate it in MATLAB and do the whole thing, and have it all done before lecture's over, I hope. Okay, so any questions about anything on the board? Or about anything else? And I'll give you a whole minute to ponder that, copy the board, think about things you want to ask. The way to think about questions is to think, as usual, what question do you wish somebody else would ask, and then do them the favor of asking it for them. Yes? Neil. Say again?
Can you sort of go through the second photograph?
This example here or this example here? Okay, so in the walking, we imagine the approximation of walking is that when one foot is on the ground, your leg is approximately straight and your hip goes approximately in a circular arc. Then the other foot hits the ground and you go in another circular arc, and the motion is a sequence of circular arcs. Okay, and this goes by a name called the compass gate. And there are a couple of reasons why you might want to call it a compass gate. One is there's this device called a compass, and it looks like a compass walking along. Another interpretation is that this is you drawing an arc of a compass, and I don't know which of those interpretations people mean when they call this a compass gate. But both cases, it looks like they call it a compass gate. So here's approximately what the motion looks like. What is the velocity of your hip as you walk along? Just before my foot hits the ground, it's fallen from a high point. Sorry, just after my foot hits the ground, I've pushed off with this back foot, and my hip is going up and forward, and that corresponds to this point right here. And that's this point right here. Then as I move up over the top here, the velocity goes from up to horizontal to down again. So the velocity goes from upwards to horizontal to down again. And then when it's horizontal, it's a little smaller in magnitude because there's energy has been lost as my body has climbed the mountain of going up over that circular arc. Then it speeds up again. Then my foot hits the ground, and some fancy stuff happens with big forces on my 2 feet, and I start to go up again. So somehow I have to jump back up here, somehow by pushing with my back foot and front foot, and I end up then back on this spot. And so as you walk along, you go around this loop, over the circular top, 2 feet on the ground, over the circular top, 2 feet on the ground. And here you see there's some kind of periodic motion. Here it looks kind of periodic in a different way. But here you see, in some sense, you're just going around some loop in velocity space. Did that answer your question? Okay. Look at the rest of the board, please, and ask another question. So all the letters on the board you should know. You should know them all and what the relationship is between all these letters. I think nothing I've done here is strictly new, but we're going to really use this stuff this semester. Yes? For which graph? For this graph? Okay, I have an x-axis, and I'm telling you here that sometimes we call it x and sometimes x1. So it's just two different notations which are used. And a y-axis, which sometimes we call x2. So sometimes we use x1, x2. And we have unit vectors parallel to these, which sometimes we call I and j, and sometimes we call them E1 and E2. And this is then showing a particle moving in the plane. And this is and at this point it's got some x position and some y position. At this it's got a different x and a y, or different x1 and x2. Does that address your question? So in principle, you should be comfortable with every term and every equation on this board. Whether you are at this microsecond, I don't know, but you should be comfortable enough so you feel like you can get there very shortly. Okay, so there's some general theorems about particles in space, about momentum and power and energy and work and conservation of energy and things like that. I think I want to wait with those until you've seen some problems, and then I'll come back and tell you those theorems, either today or next time, or you can read about them in the book. And by the way, where we are in the text is 10.1 to 3, and we're cruising right through these sections. So all in one time, you're supposed to read and understand, of course, all three of these sections. Okay, so now I would like to do an example for most of the rest of the lecture. And the example is we have a planet and a satellite, and they're gravitationally attracted to each other, and they're out there in space, and we're not worried about the near-Earth gravity. All we've got in the universe is these two things, and we want to know how this thing moves around. And we're going to, for simplicity, it's actually barely harder to do it in 3D than 2D, but just so we can draw it, and the computer code just is one shade less complicated, we're going to do it in 2D. So we're going to do 2D motion of a satellite, but if you understand it, you can do 3D in like 3 extra minutes. You can do the whole thing in 3D. So we're going to have a planet here, which is M1, and we're going to have our satellite over here, which is M2. And we'll put a coordinate system in the center of this big planet here. And this big planet is going to be so big that we're going to think about it as being still. So we could think of there's some giant skyhook holding this one in place, and all we're really going to do is watch the motion of this one. So this one we're going to assume is stationary. Its motion is so small that we can neglect it, or it's held in place. And this one is moving around. And so what we want to know is how this position R2 changes in time. So our goal is to find R2 as a function of time. How does this satellite move around this planet, or this planet move around the sun, or this star move around the center of the galaxy, or whatever the problem is like that. Okay, so how do we work this problem out? Well, you start with the free body diagram. Free body diagram of this planet here is what we need to work with. And there's some force on this planet, which is this gravitational attraction. And I'd say the first hard part about this problem is representing this force in a vectorial way so that we can do 2D mechanics with it. So we have this other thing over here, which is not part of the free body diagram, and we're interested in this force. So this force is the force on M2. Any questions about the setup of this question? Yes?
We started with R2.
How come I started with R2? Because I decided to make a simple problem with the motion of one particle really, if we're going to do this problem properly, we want to keep track of both of these particles, and we'd write F equals ma for this one and look at how they move around each other in space. But then that would have 1, 2, 3, 4 position coordinates, 4 velocity coordinates, would be 8 differential equations. So I just don't want to do it so complicated. So I'm going to hold this one still and just look at the motion of this one. So to simplify the problem, I held this in place, and I'm going to watch this one. I could have called M2 the big one, and seems like the big one should be called 1, and the smaller one 2. I don't know. What's the short answer? 1 seems like the big one, 2 seems like the small one. Did I address your question? Okay, so this is our big goal. This is what we're trying to figure out. How does this thing move? So what do we know about this force? Well, we remember from high school physics, 90% of you, I hope, that the force of gravity between two objects is proportional to the two masses, and it's inversely proportional to the square of the distance between them, which I'll just call it little r now, squared. And that's sort of right, but it's sort of wrong. Why is it wrong? Is because here we have a vector equals a scalar, and the vector just doesn't equal a scalar. So it's there's something right about the concept, but it's not right in a technical mechanics sense. We can't work with that equation. So what do you mean when you say the force is this? Well, what's wrong with this? This doesn't tell us the direction of the force. What is the direction of this force? It's in the direction of minus ER. So you can represent a force. I could have represented this a different way. I could have put here F is equal to G M1 M2 over R squared, and then implied by that would be this scalar multiplied by this unit vector, or I can use a vector notation in which I have to put the scalar and the unit vector together. Any questions about that? Yes?
Why does it have to be negative?
Why does it have to be negative? The question is, what's the direction of this thing that I drew here? ER, remember, is a unit vector in the direction of R. ER is R divided by the magnitude of R. That's what's on that board over there. And and why does it have to be negative? Because gravity is an attractive force.
So like R hat.
Say that again. ER hat is defined exactly by this equation. So it's in the direction of R. So we want a force in the opposite direction because it's an attractive force. If instead we were doing electrostatic forces, so we had here a pile of protons and here another proton, then we would have a plus sign there, and it would be what's the constant here in what? And this would be charge 1, charge 2. Right? Okay, any other questions? Signs are important though. Okay, so now we want to put this together with linear momentum balance. So for linear momentum balance, we have that the force, or the sum of all the forces, is equal to the rate of change of linear momentum. In this case, we have a single force is equal to ma, and we can write this then as A is equal to 1 over m2. And if we want to make sure that we know which point we're talking about, it's like that. It's 1 over m2 times F. And now we make in the substitution for what F is, and F is this minus G M1, 1 over M2 times the quantity G M1 M2 divided by R squared multiplied by ER with a minus sign in front. And then we can go one more step with that. And we can say then that A2 is equal to minus M1G over R squared ER. And you might ask, what do you mean by R squared? R squared is R dot R, square root, or sometimes people write it as the magnitude of R squared. And that's a dot and the dot product. Well, if we take this equation together with this equation, which is that V is equal to R dot, this is it. This is our crystal ball. That's the differential equation that tells us how this thing moves around. How does it tell us that? Is if you go back and look at this key equation back over here, take that equation to the top, it says R at t plus delta t is approximately equal to R of t plus v times delta t, exactly like in one dimension. That's just taking the top equation and rearranging it. So if we know what v is, we know what r dot is, we can march forward in time and get a new position. If we have a new position, we can calculate a new radius, we can calculate a new unit vector, we can calculate this thing, which means we know this new acceleration. And this new acceleration is the rate of change of this velocity. If we know the rate of change of velocity, we can march forward in time with that velocity. If you want to think about it in components, this v, or this v2, is equal to x2i plus y2j, and this r, or r2, is equal to x2i plus y2j. One with dots on top, one without. So we can write, if we want to think in the MATLAB component world, we can think of keeping track of this x2 and y2, and this v2, vx2, and vy2. And we can think of keeping track of a z dot, and z dot would be this vx, vy, and ax, and ay, all with the 2's, which I've left off. x2, I should call it v2x, v2, a2, 2, and the 2 should be in front of the x and y, because it's okay. So given that it's ready to go in MATLAB, do you think you can see it on this screen, or should I go for the big screen in MATLAB? Big screen. That's easy. Okay, while I'm working on big screen, you work on asking a question. Give it a minute to think about life. Touch screen to begin. Laptop. Send to center display. Too dark. Don't like that one. That's not good. Okay, yes, student. Who asked the question? Yes? What was your question? Why is r squared equal to square root of r dot r? Is that if we have a x coordinate and a y coordinate, and we're looking at some vector here r, which has here an x coordinate and a y coordinate, then the length of this vector is the length of this thing here, and by the Pythagorean theorem, that's x squared plus y squared. And if we compare that to xi plus yj, and we dot that with xi plus yj, we get this x squared plus y squared. And what you're complaining about is this square here. Is that the problem? Is that what you were complaining about?
And the other.
Oh, it's the other one you didn't like. Sorry. How about that? Does that make you happier? So don't ask the question in that dishonest form. If I made a mistake, just tell me so. Yes?
Why moving things
Say again? Why did I put this like this? So in all of mechanics, we're thinking about this crystal ball thing, about predicting the future. And we say if we know the current state and we know the laws of mechanics, we can predict the future. How do we represent the current state? It's by the positions and velocities of all the things of interest. In this case, we assume that at mass 1 doesn't move, so we need to know the position and velocity of mass 2. So the state of the system is the position of this ping pong ball and how fast it's moving and in what direction. So it's the 4 numbers, x and y position and x and y velocity. And then the crystal ball, which tells us how to predict the future, is what's the rate of change of these things. And that's the z dot, which we calculate using 1, kinematics, that the rate of change of position is velocity, and 2 is the laws of mechanics, that the rate of change of velocity is acceleration, which we calculate using F equals ma. Does that address your question? There's a joke I have to tell. It doesn't really make sense, but one can only tell jokes like this so often. So you're used to the old Professor Ruina. Today you have the Professor Ruina on steroids. Not that the class is any different, but you can't tell jokes like that any old day. You know, you're only taking steroids every now and then. Okay, so okay, so what I've done here, and I'm not going to spend a lot of time on this code, but this code is a very small modification of the code that I used for the 2 masses last week. So we have our Euler integrator. I didn't change 1 bit about this code in order to do this planetary motion. In terms of setting things up, I have to set it up with different parameters. So I have the mass 1, I have the mass 2, and I have Vic G. And now to start with, and you should do this when you write programs like this, if you wanted to know a satellite problem, you have this Vig G, which is this giant number, 10 to the 16th or 10 to the minus 16th, and you have huge numbers floating around. When you're debugging the code, use numbers like 1. So you get a sense of how the code works, so you don't have the thing spending hours or microseconds and all messing up. We have the number of steps we're going to integrate, the time span, let's say 10 units of time. Now what's different here is the initial condition I'm calling R0. It's 2 components to the vector. I'm going to say the x component is 1, the y component is 0. I have V0, 2 components of velocity. So to start with, I'm going to have this ping pong ball over here to your right and going up. That's my initial condition. Sun here, ping pong ball over here distant 1, going up with the speed of 1. That's what these 2 lines here. And I put these 2 together in a 4-element vector. And make it a column vector, and that's this list of numbers, which is initial values of x, y, x dot, and y dot. And then I just do the integration like I normally would, and then I unpack it. So we haven't said what the differential equation is yet, but after we solve the differential equation, I take the output, which is 4 columns, x, y, vx, and vy. First column is x, second column is y, third column is vx. Fourth column is Vy, and I didn't bother with the 2's because I'm not paying attention to mass 1. So just to make the code less cluttered, I just called position of mass 2, and the velocity of mass 2. Now what's the differential equation look like? This is what this course is mostly about, is you're being able to go from words and pictures to differential equations, and the key of that is only these 2 lines right here. Everything else is sort of MATLAB syntax. So what are the differential equations? What's the crystal ball that tells you how this thing moves? Is the rate of change of position is velocity. And this is now 2 equations because I've got 2 numbers stored here in R, x and y, and I have 2 numbers stored in here, vx and vy. And what's the acceleration of the thing? It's in the direction of this unit vector r, which I've defined up here. I'll show you that in a second. It's got a magnitude which is proportional to big G and this m1 and this thing which I call the magnitude of r squared. And this is the whole differential equation. which I have to pack back up into a list of 4 numbers, which is the rate of change of position and velocity, which is velocity and acceleration. So here's the first 2 numbers, Vx and Vy, and the second 2 numbers, 3 and 4, which is Ax and Ay. Now, to make this code look simple, I did a pre-calculation, and every single time step I have to do this again and again. I found the first 2 elements of z I called r, that's x and y, and the second 2 elements of z I called v. Then I take the magnitude of r, which is the square root of the dot product of r with itself, and then I have a unit vector in the r direction, which is r divided by the magnitude of r, and then I have this all put together, and this gives the 4 numbers, and this is ready to go. Now, what do I do with this is I can plot the trajectory. So I can plot here x versus y. That's a cross plot. The output is x as a function of time and y versus time, but I can plot s versus y, which shows me where it is at all different times. Or I can plot x versus time and y versus time, where I put time on the x-axis and the x and y coordinates on the 2 y-axes. Okay. Now, I don't want to suffer through this code in detail now. I'll post this code. As usual, you should not copy this code. You can use it when you're stuck, but your goal is to be able to write code like this from scratch by yourself. And if you don't go through the exercise of pounding your head against the wall and having mistakes for an hour that you can't solve and so on, you haven't really learned how to do it. So if you just start with this code and try to memorize it, you won't become functional. You will only get functional by being lost and being stuck and finding your way out of the trees. And if you're really stuck, you find your way out of the trees by looking at this code. Okay, but any quick questions about what I've done here? Or do you want to stare at any part of it? Okay, so now what is the motion of this thing? We run this thing and we get plots. And I get 2 plots because I had figure 1 and figure 2. And it looks kind of like it goes in, well, is it circles or is it not circles? You can't really tell because the axes aren't equal. So if we want to know what the orbit really looks like, we want to put axis equal. And I did put an axis equal, but I put it after the wrong plot. Okay, so I put axis equal after figure 1, not after figure 2. And then I will see what the shape of this trajectory is. And it looks kind of like a circle, and it looks kind of like the harmonic oscillator, position and velocity harmonic oscillator. Now, is that trying to be a circle, or what is it actually doing? So is that a numerical error, or is that how the thing really moves? Any guesses? All in favor of numerical error? All in favor of how it really moves? Okay, well, we can find out by just making the calculation more accurate and seeing what it does. Run it again a little more accurately, and it looks like it's trying to be a circle. And if I do it more accurately still, it'll close up to be more like a circle, but I have to sit and wait around for it. I've got my little code here that says starting at and ending at, so I can tell whether it's running or not running or what. And there it is, and it looks like now, make it 100 times more accurate, it really looks like it's trying to be a circle. So as to not waste lecture time, I'm not going to do it quite so accurate. So we'll know that when it's not quite a circle, it's trying to be a circle. We'll go back to this less accurate one, which goes faster, and we can see what these things look like. Okay, now, is that really the way things move when a planet goes around the sun or a satellite goes around the Earth? Does it go in a circle? Can it go in a circle? Okay, so it depends on the initial conditions. So let's just say instead of putting a velocity of 1 here, we put a velocity of 1/2 and see how it moves. And now it looks like it's trying to be what shape? It's trying to be an ellipse. It's not doing a very good job of it. If you didn't know this problem before, you wouldn't know whether that's really what the right answer is or the wrong answer. So you always have to check when you do numerical problems, how does the answer depend on the accuracy with which you do the calculation. And here we do it more accurately. We have to wait a long time, and it looks like it's trying to be an ellipse. And it's funny, it's an ellipse which is not centered at the origin. See, in the plot over here, I plotted x and y, and then I also plotted 0, 0 with a star. That's this thing here. So I have this star, so it's an ellipse which goes like this. So it started here It didn't start very fast. It fell into the planet, then zoomed out here and fell into the planet, and that shaped this an ellipse, or trying to be an ellipse. It takes less time than before, so I could integrate this a bit faster and look at less of the orbit. Is it running, starting at, it's not that much faster. And then if we look at the x and y position, it does funny things, like the velocity gets very high in parts of the motion as it zips around the planet here. And then what happens if I put in a big velocity here? What shape do I get? So I run it with this. It's running now, starting at. Let's just look at the trajectory shape. It started here at 1, going up, and then it goes off. Is that some big ellipse? And the answer is no. This is bigger than escape velocity, and it's working its way out here to infinity and beyond. Right. So this is a hyperbola. So depending on the initial conditions, you get an ellipse, a circle, a hyperbola. And if you give exactly, precisely the right initial conditions, you get a parabola, which is the shape which is on the boundary, just on the boundary between a hyperbola and ellipse. Okay, any questions about this numerical integration? Okay, just out of curiosity, last class, or 1 or 2 classes ago, I spent pretty much time on and I asked people afterwards, a group of people, how they thought of it. And they said, one person said, I get a headache every time you show that MATLAB. And another person said, I can't follow all the details. And so basically I got this sense that like spending 15 minutes explaining MATLAB code is not productive. Do you agree with that? Yes? Disagree with it? So some of you follow MATLAB when I do it in class, and some of you don't. If I take some code like this that I've written, let's say, and I come back a year later and I look at it, it just looks like I's and J's and brackets and letters, and it takes a while to sort of dig in and make it have some feeling. So I can see why you would have trouble with it in lecture. Anyway, that's what I wanted to say. Goodbye. See you Tuesday.